Ladies and gentlemen, welcome to Chapter 3 of the Small Hydropower Technologies program, being run by the University of Science and Technology, Kumasi, Ghana. This chapter focuses on hydrological aspects of hydroscapes, such as flow and various head measurement techniques. It will also look at geological survey to gain information on future surface and subsurface movements, storm gullies, soil and rock types as well. For flow measurements, we'll be looking at flow prediction by the area rainfall method. An estimate of average flow or discharge at any point can be made from existing records of rainfall, such as information from nearby rainfall gauge stations. The total volume of rainfall each year on the catchment determines the yearly flow or discharge. Some of this rainfall evaporates and some flows underground. It is sufficiently accurate to calculate the average yearly fluid flow, sometimes called the runoff at any point, as runoff equals to rainfall minus evaporation. In the absence of rainfall data, the following technique can also be adapted. If you have a year or two waiting for planning and finance clearance, you can immediately install a flow measuring device and monitor it as frequently as possible. You need to set up at least one rain gauge at the point of interest. Often, data in the form of ISO heights are also available. They should never be used as a single indication of rainfall records, but are sometimes useful as a check on their implications and indications. Another way of determining the flow is to use a method known as a Bayesian method. That is, by dividing the catchment area into polygons, assuming that each polygon has a rain gauge installed on it. Flow prediction by correlation method. Another way of determining the flow is by using the correlation method. In many cases, there may be insufficient rainfall records for the proposed sites. Instead, it may be possible to find flow measurement records from a nearby region or stream. If this exists, then it is likely that a flow duration curve will also be available for the Gate River. However, if the flow duration curve does not exist, then we need to prepare one flow duration curve. The correlation method will then allow you to draw up a flow duration curve for the stream in which you are interested. The steps to be taken are as follows. The first step is to make some on-site measurements of flow at the site of interest. This we call the on-gauge site. You need to take about 12 or more measurements at different times of the year at random times. Then you compare your results with the gauge site. And with the help of the fluid erosion curve, you are able to determine the flow at that particular gauge. Head measurements. There are a number of methods for head measurements. This includes water-filled tubes and pressure gauges, spirit levels, altimeters, sighting meters with spirit levels, builders levels, and the use of maps. A map could be used to estimate the head at various sites. This represents only a quick first look at various possibilities in that particular region and does not represent a careful measurement of head. Because head is the most important factor in hydropower design and costing, it must be measured accurately at all sites being costed. An accuracy of about plus or minus 3% is always required for head measurements. This slide shows head measurement by water-filled tubes. In this method, we need two people, a tube filled with water to measure the head. Now let's look at side flow measurements. The purpose of hydrological study is to predict flow. As flow varies through the year, the results of any hydrological study will always be the proper record of flow at any particular site. The hydrological study should be based on many years of daily records. The following flow measuring techniques will be applied for small hydro power schemes. The salt method technique, the bucket method technique, the float method, the propeller device method, and the stage control methods, including wear methods. We will look at one method for flow measurement on sites, the bucket method. The bucket method is a very simple way of measuring flow at any site. The whole flow to be measured is diverted into a bucket or a barrel, and the time it takes to fill the barrel is recorded. The volume of the barrel or container is always known, and the flow rate is obtained simply by dividing this volume by the filling time. However, the disadvantage of this method is that the whole flow must be channeled or piped into the container, the bucket, or the barrel. Now let's look at the geological survey of a site. The main purpose of the geological survey is to assess the best locations for future proposed civil works and to estimate their construction costs and future maintenance costs. The geological survey will always assist in determining the following. 1. Possible surface movement or loose slopes. A loose slope usually self-evident or indicated by debris collecting at this place. Civil works must be protected by stabilization of slopes above and below the works. Storm gullies. Care should always be taken when surveying to identify small gullies which may look too small to worry about, but may nevertheless become forceful torrents in a bad 10-year storm. Floodplains. Signs of periodic flooding will be seen on any site, and information of floods will be obtained from people who live nearby for a long period of time. Typical signs of flooding are low ground near the river, ponds, suspected river pond debris or river banks, or caught in bushes. Floodplains pose various risks to the hydroscheme. The river path might change, sediments build up, Sandy ground may be unsuitable for placing foundations, powerhouse, and intake structures. Landslides. Slip zones can be detected by carefully surveying for sudden steps in the hillside or cracks. A spot is found where the fault line meets the surface. Sometimes a sudden dip or rise in the path indicates a fault or a broken section of a wall. Slope stability. This is layer fault and consists of parallel faults sloping downwards the direction of the slope. Layer faulting is detected by presence of debris collecting at the foot of the slope, the exposure of layers or subsurface material on the hillside. Subsidence. This is caused by the presence of soluble rocks such as limestones and the action of water and chemicals underground. Underground water causes and dissolves rocks are indicated by a sudden appearance of streams and their sudden disappearance into the surface. A clear indication of subsidence is the presence of sinkholes. These are usually small circular 2 to 10 meters diameter depression in the surfaces, which may have a small hole at their deepest point from which water trickles or may be dry. The sinkholes are formed when limestone dissolves away to the point at which soil above collapses. Now we talk about the rock and soil types. During your survey, you need to sketch for a proposed installation area careful notes of the rock and soil types. It is worthwhile to dig inspection chambers and trenches at various points around the survey area. The purpose of these trenches is to enable you to assess 1. The suitability of the rock or soil for placement of foundations. Likelihood of movement of foundations can also be assessed. 2. Suitability of the soils and rock used as construction materials. It is well known that foundations must be laid on fine, solid rock or soil. Where these are not found at reasonable depth from the surface or found partially, piles may be driven deeper underground until firm material is found or reached.